Hi guys, this is Mr. Krieger. We're going to do a review of sampling and experimentation today, so make sure you print up the lesson. This is pretty easy stuff, but we have to go over it so it's fresh in your mind, because they do ask questions about this, so just bear that in mind. So before we look at the lesson, let's just talk about a few things. First of all, sampling techniques include SRS, which you're very familiar with. We always talk about that. That's truly a simple random sample. You know, put 100 names in a hat and pick out 50, and that's from one group, etc. Stratification, if you remember, that's where we put people into separate groups depending on qualities of those particular groups. For example, in a high school, you might stratify by grade because there might be a difference between 9th graders and 10th graders and 11th graders. So stratification would be a good technique when you know the groups are separate based on a particular characteristic. Now, cluster sampling is good to use when a particular group is a microcosm of society at large. But if you're using cluster sampling, you have to keep in mind that once you pick a cluster at random, you have to include every single individual in that cluster in your sample. So those are the sampling techniques. Now, when we talk about experimentation, sometimes you're just randomly assigning people into groups, but sometimes you're doing something called blocking, which we're going to look at in a couple of these problems. And this is a key consideration here. This is where people lose points on AP exams. Confusing stratification with blocking. Stratification is a sampling technique, and blocking is an experimentation technique. If you use the word stratification when you're talking about an experiment, you're going to lose credit, okay? So make sure you keep those things separate, all right? So we're going to now take a look at the first question here. Okay, it is let me read it, hold on. High cholesterol level in people can be reduced by exercise or by drug treatment. A pharmaceutical company has developed a new cholesterol-reducing drug. Researchers like to compare its effects to the effects of cholesterol-reducing drug that is currently available on the market. Volunteers who have a history of high cholesterol and who are currently not on a medication will be recruited to participate in the study. Just let me put my piece under here. Okay, so the first part of the question is, explain how you would carry out a completely randomized experiment for the study. Now, if you remember what we have done in the past, since we have these two treatments, we're going to want to put people into groups, into the two treatment groups, right? But what you want to say here is you want to say randomly assigned subjects. If you do not have this idea here, you're going to lose credit. It's important that you randomly assign subjects. Now, in this case, there's no placebo. You have the old medication and a new medication, so you don't want to talk about a placebo group here. If you happen to want to compare these two medications to a placebo group, like using like a sugar pill, you'd make a third branch and you could break it into a third section. But here we're not using a placebo group. So you might want to say treatment 1, which is, the old drug. And then treatment 2, which is the new drug. Okay? And then here, you're going to say compare results. And you could do that, you take the average of this and the average of this, you run a hypothesis test, etc. So that's how you would do like a very simple experiment here by just breaking into two groups. Now the next part B, it asks, how could you improve the design by incorporating blocking? Well, one thing that it mentioned in the problem is it said exercise could also work by to reduce cholesterol. So what you might want to do is you might want to do blocking based on exercise level. So first, you might want to break your thing into two groups. So block 1, before you even randomly put people, block 1 might be the exercise group. And block 2 might be the non-exercisers. Now this will be good because we'll get to see what kind of effect the drug has on people who already probably reducing their cholesterol through exercise, and we'll get to see the effect of the drug on those people who don't exercise. Then there's going to be, now you're going to be doing your random assignment. So I'll put it small here. You're going to do random assignment from that group, right? And you're going to do a random assignment from this group. And it's like you're doing 2 separate experiments. So now this is what's going to be right here. There's going to be treatment 1 and treatment 2. That's the old drug, and this is the new drug. And then you're going to compare results. And same thing here. This is going to be treatment 1. This is the old drug. And this is going to be treatment 2, and that's the new drug. And you're going to compare the results. And this is a block design because you block them based on whether they're exercisers or non-exercisers, okay? By the way, the effect of blocking is to make your results more specific. Now instead of having any old people in each different group, now we've gotten a block where it has people who are already exercising. They may not get as big of an effect from the drug, or maybe they will, but at least we will get better results when we block than when we don't block. But this is a perfectly legitimate technique. It's just that this is an even better technique. Okay, finally, can this experiment in part B be done in a double-blind manner? Remember, you want to define what double-blind means to the graders. You want them to know that you know what it means. Now, double-blind, you would tell your grader that it means that not only does the volunteer not know what treatment they're getting, which drug they're getting, but the researcher doesn't know what drug they're getting either, right? So neither the volunteer nor the researcher know. So you could definitely do a double-blind experiment here. You would have to define some way so that, people are, let's say one person makes sure to put people into blocks, and then another person makes sure that when they assign assign pills, that the person who's assigning the pill doesn't know what pill they're giving. So you could make this a double-blind experiment. You would have to make sure that the researcher who's distributing the medicine doesn't know who's getting what. Okay, so that was question number 1. Okay, question number 2. Okay. Students are designing an experiment to compare the productivity of 2 varieties of dwarf fruit trees. The site for the experiment is a field that is bordered by a densely forested area on the left. The field has been divided into 8 plots of approximately the same area. The students have decided that the test plots should be blocked, so they're doing blocking, 4 trees, 2 of each of the 2 varieties, there are 2 varieties of these dwarf trees, will be assigned at random to the 4 plots within each block. Okay, so you have you have 2 different types. So you're going to be basically having 4 trees of one type, 4 trees of the other type. 2 of each type is going to come into each block, and then we're going to randomly put them into the block. So we're going to randomly assign that, right? So we have 2 blocking schemes are shown below for consideration. For each scheme, one block is indicated by the white region, and the other block is indicated by the gray region, okay? So now it says, which of the blocking schemes, A or B, is better for this experiment? Explain your answer. Now, why don't you think this through? If we use this as a block, that means we're going to put, let's say, we're going to randomly assign trees here. So let's say the varieties are variety A and variety B. So you got an A and a B and a B and an A, and it was randomly picked. And then you're going to randomly assign trees here, and you got an A and a B and a B here. These were randomly selected. Or you could have done this, where, these are your 2 blocks. Well, it turns out that this is the better blocking scheme. Why? This block has a difference from this block. This block is close to the forest. Being close to the forest might have some positive or negative effects. Maybe the shade provided by the forest will cause the trees over here to grow less less than the trees over here because these trees are getting more light. Or maybe conversely, maybe the trees that are close to the forest, maybe this soil is more fertile than this soil, so these trees actually grow better. Who knows? But the thing is, because there's definitely a distinction between this block and this block, we want to block this way. Here, this block, there's nothing in particular that this block has that's different from this block. Two pieces are close to the forest and two pieces are far away from the forest, and so there's nothing that distinguishes the two blocks. Here you have a block which is close to the forest and a block which is far from the forest, so that would make more sense. This way you're really seeing if the being in this section has an effect compared to being in this section. Okay, so even though the students have decided to block, they must assign varieties of trees to the plots within each block. Why would we bother doing randomization? Why don't we just do A, B, B, or just pick the trees and not have any particular reason? It is always important to do randomization. Why? Because we don't want to have some sort of other underlying variable that will have an effect on the outcome of this development. In other words, maybe there's something special about the soil in this block that doesn't exist anywhere else, which is going to affect its growth. So if you purposely put a tree there, as opposed to randomly putting a tree there, that's going to have an effect on the outcome. So there always needs to be an element of randomization in an experiment in order to have, or even in a sample survey, in order to make sure those results are going to be valid. So randomization procedure is absolutely necessary. Okay, let's take a look at the next problem. Okay. Before beginning a unit on frog anatomy, a 7th grade biology teacher gives each of the 24 students in the class a pretest to assess their knowledge of frog anatomy. The teacher wants to compare the effectiveness of the instructional program in which the students physically dissect the frogs with the effectiveness of a different program in which they use a computer software program that simulates the dissection of a frog. After completing one of the two programs, students will be given a post-test to assess their knowledge of frog anatomy. The teacher will then analyze the changes in the test score to see if there was any, if one program was better than the other. Describe a method for assigning 24 students to the two programs of equal size that allows for a statistically valid comparison. So this is basically, the first one is just a basic experiment design. So you could very simply randomly select 12 students to go here. So you're going to do a random assignment. Got to say that. Random assignment. And this is going to be for the one treatment. This is going to be for the actual frog dissecting. This is actual frog dissecting. And this will be virtual frog dissecting, right? Okay, so here we're randomly assigning into those two groups. Okay, we want to make sure that, there's some method for randomization. You could actually describe it. You might want to give a little description of how you're going to, assign each student in the class a number from 1 to 24. And then the first 12 numbers that you pick out of a hat, pick those people for the frog dissection group, and everybody else goes into the virtual dissection group. Okay, and then you'll do a regular comparison. Okay? Suppose the teacher decided to allow the students in the class to select which instructional program on frog anatomy, whether they pick physical dissection, actually doing the dissection, compared to the simulation. So they get to select which program they're going to use, whether they're going to do the actual dissection or the virtual dissection. And what happens is 11 students choose this group and 13 students choose this group. How might this self-selection process jeopardize a statistically valid comparison of the changes to the test scores? For the two instructional programs, it says provide a specific example to support your answer. Now, there's always a problem when there's self-selection. There could be some specific reason why some people want to pick the actual frog dissection compared to this group. And if that's the case, then you might have some qualitative differences in these groups. Now, if you wanted to give a concrete example, you might want to argue something along these lines. You might want to say, well, let's say the people who already know a lot about frog anatomy are people who have studied a lot and they actually love frogs. And so these people who really love frog anatomy are putting themselves into the virtual frog dissection, because they don't want to actually dissect a real frog. They have too much respect for actual frogs. So now, a lot of people in this group have self-selected who happen to know a lot about frog anatomy. Well, in this particular case, what's going to happen is this group is not going to improve a lot. Why? Between their pre-test and post-test scores. Because they already know a lot about frog anatomy, their score is not going to improve much. And it's not because of the virtual frog dissection. It's because they already know a lot about frog anatomy compared to this group. So in essence, what's happening is you have a situation in which people have self-selected here, and you're getting results or answers that have no impact based on the program they're using, but because they've self-selected into that. So that's problematic. So the randomization is essential, or else you can get qualitative differences in the types of groups you're dealing with. Okay? Let's take a look at the last question. The first three questions had to do with experiments. This last question has to do with surveys and conducting sampling techniques. So let's take a look here. A local school board plans to conduct a survey of parents' opinions about year-round schooling in elementary school. The school board obtains a list of all families in the district with at least one child in an elementary school and sends the survey to a random sample of 500 families. The survey question is provided below. A proposal has been submitted that would require students in elementary school to attend school on a year-round basis. Do you support this proposal, yes or no? Now, of the 500 people, they received 98. They received responses from 98 of the 500 people selected, and 76 of those said they are in favor of year-round schooling. Of the 98, 76 are in favor. Let's see what percentage that is. So we got 76 over 98. That's like almost 78% of people are like seem overwhelmingly in support of year-round schooling for their elementary school children, right? Okay, so based on the outcome, the local school board concludes that most of the families with at least one child would prefer year-round schooling. A, what is a possible consequence of non-response bias for interpreting the results of this survey? Now, people who might be extremely in favor of homeschooling are probably the ones that are much more likely to even return this survey. So that's biasing the outcome, because now you're saying, oh, 78% of the people seem to be in favor of homeschooling, the year-round schooling. But really, that's only because less than a fifth of the people responded. Maybe if you got the results from everybody, the result will be quite different. So this is a self-selection, which is going to have bias for that reason. Now, Part B says someone advised a local school board to take an additional random sample of 500 families and use the combined results to make their decision. Would this be a suitable solution to the issue that we just talked about in Part A? Not really. We're going to have the same issue with this group, where out of those 500 people, only the people who are really strong supporters of this or are really strongly against this are going to respond, which means that the people who really have not such strong opinions are not going to really return the survey. You're going to have the same kind of bias that you had in Part A. So now Part C says, suggest a different follow-up step from the one suggested in Part B that the local school board could use to address the bias issue from Part A. Well, one of the best things you could do is for the 402 people who didn't respond, you're going to want to send them more mailings, call them on the phone, try to get a lot more of these people from your original group to respond. The more of the original people you get to respond, the more accurate your results are going to be. So that really is what you're going to want to do. Send out more mailings. Try to get as many of these non-responders to respond. That will improve the accuracy, take away the bias. Okay, the homework is the questions that follow this. All right, good luck with that.